Hello, welcome back. Now that we've had some practice with sigma and pi notation, let's talk about how we can manipulate the different sums and products that we see. First, we'll talk about sigma notation. In general, sigma notation behaves the way we want it to behave. If we take the sum, where k goes from 0 to n of a sub k plus b sub k, we can rewrite that one sum into two sums. The sum from k goes from 0 to n of a sub k plus the sum where k goes from 0 to n of b sub k. Similarly, if instead of this being a sum of a sub k and b sub k, instead if it's a difference of a sub k and b sub k, then we can have a difference of the larger sums. Now let's say we want to take the sum of a series where each term of the series is a constant multiple times a sub k. When we have such a constant multiple, we can just bring that constant multiple outside the sum, which, if this constant multiple is a positive integer, then we could see that as m copies of the sum of a sub k. Another manipulation we might do with summations is with the indices of the summations. What we recognize is that summing the terms of this series, when we start out at p and go up to q, and then go from q plus 1 up to r, is the same as starting at p and going up to r. And so when we have two summations, one that starts at p, goes up to q, and the next one starts at q plus 1 and goes up to r, we can combine those two summations into one summation that goes from p up to r. Often we'll use this in reverse by subtracting one summation from the other. Let's do some examples. When we have a summation that itself is the sum of some terms, we can break this summation into three sums. The sum from I equals 1 to n of 6i squared minus the sum from I equals 1 up to n of 5i plus the sum from I equals 1 up to n of 1. Now, when we have a constant multiple, we can bring those constant multiples outside the summation. And we get 6 times the summation from I equals 1 to n of I squared minus 5 times the summation for I goes from 1 up to n of I plus the summation from I goes from 1 to n of 1. Now, each of these three summations are the special sums that we saw in the last video, and so we can write the answer as 6 times n plus 1 times 2n plus 1 over 6 minus 5 times n plus 1 over 2 plus n. And so this is an expression that evaluates this sum. Let's do one more example. Let's consider the sum from k goes from 10 to 30 of 4 over 3 to the k. This is a geometric series, but the index starts out at 10 instead of at 0 or 1. So let's rewrite this summation as a summation where k starts off at 0 and goes up to 30 of 4 over 3 to the k, and subtract off the other terms, the terms from k equals 0 to 9 of 4 over 3 to the k. And so by doing this, what we're doing is we're taking the terms that go from 0, 1, 9, 10, 11, up to 30. And what we want is the numbers from 10 up to 30. So we take all the terms from 0 up to 30 and we subtract off the ones from 0 up to 9. These two expressions are geometric series, and we are able to apply the formula that we have for geometric series. The initial term is 4 over 3 to the 0, so 4 over 1. The common ratio is 1/3. And so the formula gives us 4 minus the next term, which is the 31st term, 4 over 3 to the 31, over 1 minus 1/3. And this sum is similar. This initial term is the same, the ratio is the same, and so we get 4 minus 4 over 3 to the next term, 3 to the 10th, over 1 minus 1/3. and we subtract those two values. I'm going to factor out a 4 first, so I get 4 times 1 minus 1 over 3 to the 31st over 2/3 minus 4 times 1 minus 1 over 3 to the 10th over 2/3, which we can write as 6 times 1 minus 1 over 3 to the 31st minus 6 times 1 minus 1 over 3 to the 10th, which simplifies to 6 times 1 over 3 to the 10th minus 1 over 3 to the 31st. Let's stop there for now. On to the next video.